global correspondences. Okay, so some general piece of notation. So f over qp is a finite extension. This ring of integers O, in there I fix a uniformizer pi and k is a residue field. And furthermore, I need the Wehl group, WF. And in there, I consider the sort of positive part, WF plus, which is to be the set of all elements tau that project to a positive power Frobenius on the residue field. Geometric Frobenius. Okay, so the first part I take just for simplicity that I take f equal to qp. And what I'm looking for is a local geometric object that realizes the local Langlands correspondence. Realizing. So if you're just interested in supercuspidal representations or on slightly more general ones, then you can take the Lubin Tate tower. Which is just the moduli space of one-dimensional formal groups of height n. I mean class level structure. And I would propose that if one is looking for realization which works for all pi, one should be looking at the moduli space of one-dimensional formal p-divisible groups. Of height n. Now this is quite an ugly object. It's a pro-Artin stack and it's not easy to get your hands on it. But one thing that I can do, this one I want to explain. So the aim is to construct one element in this positive part of the Wehl group. The element f tau of the Bernstein center of GLnF that acts through the scalar trace of tau on the associated Wehl group representation on any irreducible pi. So here sigma of pi is the Wehl group representation underlying the Wehl-Denis representation. And the basic construction goes like this. Can everybody read this when I write on this blackboard? Probably not. Okay. So I will stay in the middle. The right part's okay. Okay. So basic construction goes like this. We have this moduli space. This gives rise to a sheaf of vanishing cycles on the special fiber, which in turn gives rise to a function on the fp to the r value points. And this is closely related to this element of the Bernstein center. Let me make this more precise now. So assume f tau, this element tau of the Weyl group projects to the rth power of geometric Frobenius. So r is some integer which is at least 1. And now an fp to the r point of this moduli problem is just given by a p-divisible group of the type we consider over fp to the r. So take a one-dimensional p-divisible group, which I call h bar over fp to the r of height n. And then by Dieudonné theory, h bar corresponds to an element delta living in the following double coset for GLn ZP to the r. But it's not uniquely defined. It's up to sigma conjugation by GLn ZP to the r, where the Dieudonné module of h bar is just given by the underlying module. You trivialize, it's just ZP to the r to the n. And the Frobenius is given by delta sigma. And in all of this, I use sigma to denote the absolute Frobenius of ZP to the r. Okay. Now we look at the neighborhood of this point inside the moduli space. We take the deformation space of h bar. And over there we have the universal deformation, which I call h. And because deforming a p-divisible group is unobstructed, you can easily show that this ring is just abstractly isomorphic to a formal power series ring over ZP to the r in n-1 variables. Now we take the coverings, trivializing the Tate module as usual. So parameterizing Greenfeld level p to the m Greenfeld level p to the m structures. So this means explicitly sections x1 up to xn in the p to the m torsion of this universal deformation, such that they generate this module in some sense. And explicitly this means that if you take the Cartier divisor associated to sort of the sum of all these points, then it's the same as the Cartier divisor associated to this p to the m torsion. So this is a finite Galois cover with Galois group GLn Z mod p to the m. Talon generic fiber. So this is basically just the usual construction of the lumen Tate tower, except I should again point out that I take a general p-divisible group and not only the case of a formal group. Although this is clearly the most interesting case, but I really want all of them. Okay, and then we take the nearby cycles in the sense of Berkovich. And in fact, we take the global sections on them on the special fiber. The special fiber is just a finite set of points, the reduced special fiber. And taking the global sections means just taking the sum of all the stalks at these finite set of points. And then you take the union over all M. And so this is Berkovich nearby cycles. Okay, so one basic fact is that these sheaves are the cohomology groups are, I should say, we have an action of GLn CP on them and of the Weyl group of QP to the R, because all the objects are defined over ZP to the R. And so the Ice cohomology group is a smooth admissible representation of GLn. A continuous representation of the Weyl group. And these sheaves vanish outside the range between 0 and n-1. So in particular, it makes good sense to talk about the alternating sum in a Grothendieck group of such representations. And then we define a function So basically, we want to take the trace of this element tau that we fixed on the nearby cycles. However, the space is infinite dimensional, so it does not make sense to take this trace. So we have to fix a sort of cutoff function h on the GLn factor. So, and we take this with values in Q. And then we define a function phi tau h, which is defined on GLn QP to the R with values in QL. In fact, has support on this double coset that came up before. And we just do the canonical thing. It is a trace of tau times h acting on these nearby cycles, where delta corresponds to h bar. Now, a priori, this is a pretty weird function because first, it only takes values in QL, not in Q or something. Second, it is not at all clear how it depends on delta. And, well, that's about it. But one can show that, in fact, this function is locally constant and takes values in Q independent of L. Let me just say a few words how to prove this. So the basic ingredient is that one can view this deformation space of the whole p-divisible group also as a versal deformation space of its p to the m torsion. Which in this case is a statement due to Igusa. But if one would try to make this whole thing for general fields F, as I want to, then the exact analog fails, but there's a slightly revised version due to faultings which is true. So in the ramified case, one really needs this version of faultings. And so this implies two things. And the first thing is that these rings RH bar and M this depends only up to non-canonical isomorphism, of course, but it's not a problem, on the p to the m torsion, which then shows that this function is locally constant. And the second thing is that it also implies via Artin's approximation or algebraization theorem that these rings RH bar M are algebraizable. And this is on the one hand the reason for this admissibility of these representations. And on the other hand, it implies by result of Mieda on independence of L that this function is independent of L. Okay, so we get a nice function, but a priori it lives on the wrong group. So we do what we can do. So we just take the transfer. Meaning that the orbital integrals of this function are related to the twisted orbital integrals on the function, on this x tangent. Okay. So now for general f, we can do pretty much the same thing. So we get functions f to h living on GLn f for tau an element in this positive part of the Weil group, and h function on the maximal compactor. Okay. So now I can state first main theorem. The first part is that for any irreducible representation pi of GLn f, there exists a unique n-dimensional representation of called rec of pi of the Weyl group, such that for all tau and h, the following identity holds true. The trace of f tau h on pi is the same as the trace of tau on rec pi times the trace of h on pi, which in some sense amounts to something very closely related to this identity. That if you take the convolution of this function f tau on the bandstand center that I introduced and convolve it with this function h, which is sort of a cutoff function, you get this function. At least it has the same orbital integrals. And there's one other slight inconvenience, is that the representation is only almost the correct one. So we have to twist it a little to get the real Langlands correspondence. So Tay twists by n-1/2. And with this normalization, we can prove that if pi occurs in an induced representation, normalized induction from a parabolic, then the associated Weyl group representation is just a direct sum. Note that I ignore the monodromy operator completely in my talk. I mean, you can always just afterwards plug it in, but I say nothing about it. The third part is that you get a bijection between the supercuspidals and the irreducible representations. And finally, the last part is that this bijection is really the Langlands correspondence. So it's compatible with everything, twists, duals, etc. And then L and epsilon factors.
Is R allowed to vary the integer R?
Yes, it's allowed to vary, yes. So I really have this function for all tau which project to a positive power of Frobenius, and this is enough to detect the Weyl group representation. If you know the trace of tau and the representation for all tau in this subset.
R, you get already a bijection, right? Or
No, this statement is really for all tau. I mean, for all tau and not just those which project to a fixed power.
yeah, but R, you fix it? Or
No, it varies.
In the unicity of reciprocity of pi, so
I mean,
do you impose reciprocity of pi to be semi-simple?
yeah, this is over C everything. And over C there cannot be something non-semi-simple. Ah, sorry, yeah. Yes, sorry. Frobenius semi-simple. I'm sorry. Yes. Okay. Now in the second part, I want to explain how to get this bijectivity statement in 3. And well, usually one makes use of NER's numerical local Langlands. And, or in fact, a closely related statement, which is that if you start with a supercuspal representation of GLnF, then there exists a finite extension such that the base change of pi from f to f prime is not supercuspal. Which means that you write this as an extension of cyclic extensions, and then you apply Arthur-Clausel's base change. And you can find a series of cyclic extensions such that if you do this base change on and on, then it will not stay supercuspal. And so what I can do is I can prove the following lemma, and I will explain the proof afterwards. I can show that if sigma of pi has invariance under the inertia subgroup, and say n is at least 2, which is the only interesting case for this business, then pi cannot be supercuspal. So why does this prove the desired statement? Consider this base change. Then one can show that the representation attached to pi prime is just the representation attached to pi restricted to the Weyl group of ff prime, which you deduce from local global compatibility. And so,
I just want to ask a general question about, once you prove part 1 of your theorem, do you just use part 1 in the following parts, or you use the
well, yes, I first use 1 and 2, and then I prove 3.
But once you prove 1, can you then forget the construction of rect pi? I mean, does the
yes, I can completely forget about that. So you could translate this new proof of the bijectivity of the correspondence also in terms of the other characterizations of the correspondence. I mean, if you somehow know some formal properties of this correspondence, pi goes to rect pi, plus this statement that is somehow not really connected to this characterization, then you can show bijectivity.
Right, but you're using local global compatibility. It doesn't suffice simply to know the characterization.
Yes, I mean, I know a little bit more. I mean, I just want to. Yes. So there exists an f prime over f such that sigma of pi has invariance under inertia. So this implies then that sigma of pi prime has invariance under the inertia. But if this lemma is true, then this shows that pi prime is not supercuspidal anymore. So what we want to do is we want to describe the inertia invariance of sigma of pi directly. And this is more or less equivalent to a precise description of the vanishing cycle sheaves, but only their inertia invariant part. And one can get this by taking the derived invariance under inertia. And now this can be done by applying two things. The first thing is the structure of these rings, or more precisely of their algebraizations. So they are regular. And furthermore, the special fiber has some good properties. It has a stratification into locally closed subsets. Zi, such that all of their closures are regular. So at first sight, it might look a little bit like semi-stable reduction or something. But I mean, in fact, it can be much worse. So I mean, you can have non-transversal intersection, and moreover, you can have high multiplicities of the irreducible components. Yes. And the second thing is that in this situation, you can always describe the desired thing. And this is an application of Grothendieck's purity conjecture. As proved by Thomason and Gabber. Okay. And using this geometric input, you can then compute the inertia variance of the associated Galois representation and then proceed to prove the bijectivity. And so now I come to the last part of my talk, which is on local global compatibility. So the first part of the argument works in rather large generality, and I try to explain this now. So I take a proper projective PEL Shimura variety. Defined over this reflex field E. And the reductive group is occurring is called G over Q. And let me fix a maximal compact open. KP naught inside of GQP. A place of E above P, and furthermore let me fix models of these Shimura varieties over the ring of integers. And somehow satisfying a moduli description, having a moduli interpretation. I mean, one has to make some more precise assumptions. So one case where everything works is, for example, if the PEL data are unramified at P. So this gives rise to this hyperspatial maximal compact at P. And a canonical model over the ring of integers. But in fact, in the case that one has to apply it in order to get the full local global compatibility here for general fields F, it does not quite fit into this framework of unramified PLA data, but still the argument works. And for general level inside of this fixed maximal compact, we define an integral model of the corresponding Shimura variety just by normalization. So in particular, we have a finite projection map to Shimura variety without level structure. Or maybe I should call it finite. And so the aim is, if you fix an element in the veil group of this local field, as before, projecting to a positive power of geometric Frobenius, a function on this maximal compact at P that I call H again, and any function away from P. Give an expression for the trace of tau times H times Fp on the cohomology of, sort of the direct limit for K of the cohomology of the Shimura variety over E bar, its coefficients in QL. Or also other local systems, but I would ignore that. So if you fix this level K lower P times K upper P is small enough, depending on H and Fp, then in fact you can rewrite this trace as a trace of some correspondence on the cohomology at one level, but then you can go on and rewrite this as the trace on the cohomology of the special fiber with values in the vanishing cycles. And then you can use a projection to rewrite this as a trace of this correspondence on the Shimura variety with grid reduction, so to say. With values in pi lower star of the nearby cycles. And now we apply the Lefschetz trace formula to see that this is in fact sum over all fixed points of the correspondence of a local correspondence acting on the stalks of this sheaf. Now, because we are working at this maximal compact level, this is just the usual correspondence that one also considers in the context of the trace formula applied for the maximal compact. So Kottwitz has also already given a description of the fixed point set. And roughly, if one partitions it into isogeny classes, then the isogeny classes are parametrized by certain triples gamma naught, gamma delta, where gamma naught is an element in G of Q, gamma naught is an element of G away from P, gamma, and delta is an element of G, so as in QP to the R. and which in fact corresponds to the p-divisible group at X. In the same way that I had associated to a p-divisible group an element delta in the group in the beginning of the talk. And furthermore, this expression that we have here by Berkovich, it only depends on the completion of this scheme at the point X. Because Berkovich can define vanishing cycles just for complete local rings and shows that they agree with the usual ones in the situation. And by the Serre-Tate theorem, we know that the completion of this Shimura variety at this point X depends only on the p-divisible group at X. So in other words, on delta. So we can just rewrite, so we can just define an analogous function phi tau h for this Shimura variety delta as sort of the trace as before. And then this term here just equals this function of delta. Okay, and now we can just repeat all the arguments of Kottwitz and arrives at the following expression in the cohomology of the Shimura variety is given by a sum over such triples of some volume factor times the orbital integral of this function away from P times the twisted orbital integral of this function at P. So just the same kind of expression that you get for maximal compact level structure, with the only difference being that this function is somehow inexplicit. I mean, you can't compute any value of it. But still, there is such a locally defined function, which is already something quite strong, as I want to explain now. So let now G be a unitary group. So we consider the situation as in the book of Harris-Taylor. So G is a unitary group of signature 1 n minus 1, and it's split at P. So that it locally gives basically GLn. I mean, there's an extra GM factor which somehow floats around, but so basically in this case we get that this function phi tau h is just this function that we have considered before. And in this case, one can apply the process of pseudo-stabilization and applying the trace formula and so on, one does not have to deal with endoscopy in this case, to arrive at the expression that this is equal to a sum over automorphic representations of some multiplicity times the trace of this function f tor h times some function, this function away from p times some function at infinity. And using Matsushima's formula, which expresses the cohomology of the Shimura variety in terms of automorphic representations, you can then go on and rewrite this as a trace of f tor h times f upper p on the same cohomology group. I think there's one normalizing factor 1 over n here. Okay, what do we do now? We have this function f upper p, which is we are free to choose, and using Clausel's space change, from G to GLn, plus strong multiplicity 1 for GLn. One sees that one can cut out a single representation by using only this operator away from P. Because one can show that the automorphic representation, its P part is already determined by its part away from P. So what we get is that the trace of Tor times, leave place here, times H on the pi isotypic component times the stuff at P is the same as, well, there's some normalizations, the dimension of this isotypic part divided by n, times the trace of f tor h on this local representation pi p. And the left-hand side can also be decomposed as a product. Okay, but now you see that this is just precisely what defines this representation rec pi p. So we get that if you take this isotypic component, normalize it correctly to give it dimension n, and restrict to the local Dirac or Weil group, and probably semi-simplify, then what you get is just the representation attached to pi p. And this then gives you exactly the local global compatibility result as in the book of Harris-Taylor. There you start with some self-dual representation of GLn, some additional assumptions, then use Clausel's space change to cook up some representation of a unitary group, then takes an isotypic component in the cohomology of the corresponding Shimura variety, and that's the global Gauss representation that you get. And what this shows is that if you restrict to the local ones, you really get the local Gauss representation. Okay, that's all I want to say.